In this video, we're going to talk about aromaticity in compounds other than benzene. Okay, so first a review on the requirements that need to be met in order for a compound to be aromatic. We need to have a ring with overlapping p orbitals, and then it also has to meet Hückel's rule. So the number of pi electrons, we either need an odd number of pi electron pairs, or what I usually use is the 4n plus 2 rule. So we need 4n plus 2 total pi electrons, where n is an integer, anything from 0, 1, 2, 3, 4, etc. Now, we talked about anti-aromaticity in previous videos, and this is sort of the opposite of aromaticity. If something is anti-aromatic, it has unusual instability. The requirements that we need for something to be anti-aromatic is we also need to have the overlapping p orbitals, but then the number of electrons that we need is 4n total pi electrons. Now, compounds don't have to be aromatic or anti-aromatic. Most compounds, in fact, don't meet criteria 1. They don't have rings of overlapping p orbitals, and so they're simply said to be non-aromatic. Now, we saw an example in the last video. Many compounds can avoid being anti-aromatic by distorting or changing their geometries. So if they can distort enough so that they no longer have the overlapping p orbitals, then they don't have to be anti-aromatic. And because anti-aromatic is special instability, right? Molecules don't want to be anti-aromatic if they don't have to. So the first class of compounds that are potentially aromatic that we want to look at are called annulenes. And so these are rings that have overlapping p orbitals, and in fact, benzene is 6-annuline, right? So we know that it's aromatic. 10-annuline is potentially aromatic, and so we have a ring, we have overlapping p orbitals, and when we check the number of pi electrons, we have 2, 4, 6, 8, 10. So to see if that meets Hückel's number, subtract 2 and then see if the result is divisible by 4. So 10 minus 2 is 8. 8 is obviously divisible by 4, so it appears to meet both criteria for aromaticity. Now, obviously life is sometimes more complicated than it first seems. This appears to meet all the criteria for being aromatic. One problem we have is with the geometry. So these two carbons are sp2 hybridized, so they have 120-degree bond angles, and we're only seeing 3 bonds, so there's a hydrogen that we're not seeing, and those hydrogens must be pointed in this direction. So we have these two hydrogens that obviously overlap one another, and so aniline, to prevent this serious steric interaction, has to distort its geometry significantly. And so what that does is it doesn't allow for the overlapping of the p orbitals, and so it is in fact, even though it appears to meet the criteria, it's not actually aromatic. Now 14-annuline, again we've got a ring, we appear to have overlapping p orbitals. In this case we have 2, 4, 6, 8, 10, 12, 14. Right, 14 minus 2 is 12. That is divisible by 4, so it also meets Hückel's number. And then in this case, right, it also has these hydrogen atoms, but it's now big enough that the hydrogens are far enough away, and even though its geometry distorts a little bit, it's still an example of an aromatic compound. So far, we've just considered neutral compounds, but ions can also be aromatic. And so if a neutral compound doesn't meet Hückel's number, by taking away or adding an electron, we might be able to achieve Hückel's number, thereby making that ion aromatic where the neutral compound was not. And an example of a 5-membered ring is one case where we can achieve aromaticity by making a negative ion. And so if we have a carb anion here, that carbon is going to be sp2 hybridized. It's going to have 3 bonds and 1 lone pair. Right, there's a hydrogen pointing out here, planar, that we're not showing. And so this lone pair is going to be in an unhybridized p orbital. And so it's then overlapping with the p orbitals on these other atoms. And so we meet the first criteria. We have a set of overlapping p orbitals. And then when we look at Hückel's number, we have 2, 4, 6 pi electrons. So that's the same number as benzene. So we satisfy Hückel's rule. And so this compound is in fact aromatic. We can also see it if we draw the Frost circle. We have 6 pi electrons, so 1, 2, 3, 4, 5, 6. So all 6 pi electrons will fall in bonding molecular orbitals that are lower in energy than the atomic p-orbitals. And so this absolutely seems to meet the criteria for aromaticity. Now, another way to sort of confirm that we have overlapping p-orbitals is the fact that we can draw all of these resonance structures, right? In each case, we have an allylic pi bond. And we know that resonance structures stabilize anions. This was particularly important in the acid and base chapter that we did last semester. But just with the resonance isn't enough to explain the stability of this anion. And without its aromaticity, we wouldn't see some of the properties that this anion and its neutral counterpart have. As an example, when we thought about how strong an acid is, when we're doing this qualitatively, we often looked at the stability of the anion that was produced when it lost a hydrogen. And because of the extreme stability of this anion, not only due to resonance, but due to the aromaticity that we talked about on the last slide, because this anion is so stable, that makes this compound an unusually strong acid. Now, pKa of 16 may not seem that strong, but if we think a regular alkene or an alkane have pKa's of 44 to 50, right? This having a pKa of 16 is really low for a hydrocarbon. And that is due to the extra special stability of this anion that is aromatic. So we saw that for a 5-membered ring, when it became an anion, so it went from 5 p electrons to 6 p electrons, it then achieved Hückel's number and was aromatic. For a 7-membered ring, it would normally have, or potentially have, 7 p electrons. But if we make the positive ion, right, that'll drop it down to 6, which is Hückel's number. And so we might expect that C7H7 plus would be aromatic. So it certainly meets the first criteria. We have a ring with overlapping p orbitals, as evidenced by all of these resonance structures that we can draw. And if we look at the number of pi electrons, we have 2, 4, 6. And so that's Hückel's number. So this absolutely seems to meet the criteria for aromaticity. And in fact, this ion is aromatic. So just for some practice with Frost circles again, let's draw the Frost circle for C7H7 plus to confirm what we've already seen from the last slide based on the fact that we have overlapping p orbitals. We meet Hückel's number of electrons. Let's draw the Frost circle to show that it is in fact aromatic. So I've helped us out a little bit. I've drawn the molecule in the format that we want for the Frost circles. And so where these carbons are on the ring is where we're going to put our energy levels. All right, and the halfway point on this molecule is going to be through here. So we'll do a dashed line. This is where the energy of the atomic p orbitals would be, halfway in the middle of the circle. And then we have 2, 4, 6 pi electrons. So 1, 2, 3, 4, 5, 6. And so this absolutely confirms what we said on the last slide. It meets the criteria for aromaticity, and we can confirm that with the Frost circle because, again, all of the pi electrons are in bonding molecular orbitals that are lower in energy than the atomic p orbitals. And we also have all closed electron configurations. There are no unpaired electrons. All right, now we've seen how ions now can be aromatic. It turns out heterocycles can also be aromatic. And so carbons other than carbon or hydrogen can be part of the aromatic ring. And I think we'll most often see this with nitrogens and oxygens. And here are two different examples of nitrogen-containing compounds that are in fact aromatic. In the case of pyridine, we have this lone pair, but it's actually not part of the aromatic ring. If you remember, an atom can only have one unhybridized p orbital when it's part of a ring, when it's sp2 hybridized. And because this nitrogen is already participating in a double bond, that means the lone pair is in an unhybridized sp2 orbital. And so it's sort of sticking out in the plane of the molecule, right? It doesn't have the right orientation to be part of the pi electrons. And so this atom does have alternating p orbitals. It has 2, 4, 6 pi electrons, so it meets both criteria for Hückel's rule. So in this case, it is hybridized, but the lone pair on nitrogen is not involved in the aromaticity, or in the aromatic ring. In the case of pyrrole, it also has a lone pair, right? But in this Lewis structure, it's not participating in a double bond, and so this nitrogen-carbon bond and nitrogen-carbon bond and nitrogen-hydrogen bond, those account for the sp2 hybridized orbitals. And so this lone pair is delocalized. It's in an unhybridized p orbital. And so in this case, the lone pair of nitrogen is participating in the aromatic ring. And so we again have alternating p orbitals. We have 2, 4, 6 pi electrons. And so this compound also meets the criteria for aromaticity, and it is in fact aromatic. So it's kind of interesting to compare the properties of these two compounds where the lone pair is, in this case, not involved in the aromatic ring, and in this case where the lone pair is involved in the aromatic ring. Normally, we think of lone pairs on nitrogens as being fairly basic, right? They're pretty good proton acceptors, giving us the protonated ions. Now, this can happen in both cases. But remember, the larger the pKa, the weaker the acid. The smaller the pKa, the stronger the acid, right? And a stronger acid is sort of not happy in its current situation. It wants to give up one of those protons. And so you can see this compound is quite a bit less acidic than this one based on their pKa values, right? And the reason is, in this compound, the lone pair is not involved in the aromatic ring. And so it can accept that hydrogen and still be aromatic. Right? In this case, the lone pair is involved in the aromatic ring. It's needed for aromaticity. And so when it accepts that hydrogen, right, those electrons are no longer in an unhybridized p orbital. Now we have an sp3 hybridized nitrogen, and so those electrons are no longer available for aromaticity. We now have a Hückel number of 4, right? So this compound is not aromatic, and so it's not happy with that situation. It really wants to give back that hydrogen, reform this neutral compound so it can regain its aromaticity. Where this one is happier remaining as the acid because it's still aromatic whether it has that hydrogen or not. All right, the last type of aromatic compounds that we want to consider are called polycyclic aromatic compounds. Now, Hückel's rule is only intended to identify aromaticity in single ring systems. However, many polycyclic aromatic hydrocarbons, you'll often see this abbreviation PAHs, are known to exist and they're known to be aromatic. So if Hückel's rule doesn't work, how can we potentially identify these? Well, they're very often composed of fused benzene rings. So naphthalene is a common example. Anthracene, also fairly common. And then we have the phenanthrene here. So anytime you see fused benzene rings, there's a pretty good chance that that compound is going to be aromatic.